All right, welcome back. So let's just jump right in. We've got these AI models that are, basically geniuses. They can write code, they can compose music, they can analyze incredibly complex data. But here's the thing. How do we get them to actually do stuff in the real world? That's what we're going to break down today. The entire journey from a single, simple digital neuron all the way to the sophisticated AI agents that developers are building as we speak. So picture this. You've got this amazing AI assistant, and you ask it to draft an email. It can write beautifully, for sure. But what if you need it to pull some numbers from a report you just saved and check your calendar for a good meeting time? Well, it can't, not on its own. It's effectively trapped inside a digital box, completely cut off from your files, your apps, your APIs. It has all this knowledge, but no hands. And that's the fundamental problem every developer in this space is trying to solve. And this right here, this is what we call the AI in a box problem. And look, solving this is the challenge if we want to build AI applications that are genuinely useful. We don't just want an oracle we can ask questions to. We want a partner, an agent that can help us get work done.
Okay, so what is an AI agent, really? Well, it's not just a passive brain in a jar. It's an AI that can actually perceive its environment, process what's going on, and, this is the most important part, take actions all by itself to achieve a goal. It's this ability to act, to not just think but to do, that unlocks everything.
So how do we spring the AI from its box? This is where something called the Model Context Protocol, or MCP, comes into play. You can think of it as a universal connector, an open standard designed specifically to let AIs talk to the outside world in a safe, standardized, and really efficient way. Now, to really get why MCP is such a big deal, you have to understand the total nightmare scenario it fixes. It's called the M times N problem. Let's say you have M number of AI models and N number of tools or APIs. Before MCP, you had to write a custom piece of code for every single connection. This just explodes in complexity. It's an absolute disaster to maintain. And wow, you can really see the difference here, can't you? On the left, that's the old way. A tangled, chaotic mess where everything is brittle and breaks if you change one thing. But on the right, that's the world with MCP. It acts like a clean, simple hub. You plug your model in once, you plug your tools in once, and they can all talk to each other. Your M times N mess just became a simple M plus N problem. That is a massive game changer. The best way to think about this, the analogy that really sticks, is that MCP is basically the USB port for AI. Seriously, it's a universal standard that just works. You don't need a different shaped plug for your mouse and your keyboard and your hard drive, right? You just plug it into the USB port. That's the kind of elegant simplicity MCP is bringing to the table. So, MCP pulls us off with three core ideas, three primitives. First up, you've got prompts. These are controlled by the user. Things like, summarize this for me. Next are resources. These are controlled by the application, and it's data the AI can read, like a specific PDF file or an entry in a database. And finally, the most powerful one, tools. These are controlled by the model itself. They're actual functions the AI can decide to run on its own to take an action, like send an email or query the database. All right, so that's the big idea. But what does this actually look like when you're writing code? When you're an engineer with a keyboard? Let's get practical and walk through how this protocol works with some real code. And you'll be happy to hear the flow here is super clean, super simple. First, your main application kicks things off. It starts up an MCP client, which then connects to an MCP server. The server then just announces, hey, here are all the tools and resources I've got, and that's it. From that point on, your app can just call those tools or read those resources whenever it needs to. And check this out. Look how clean this is to actually build. This is a basic MCP server in Python. You just import the library, create an instance, and then you use these simple decorators. See that @mcp.tool? Boom. Just like that, your add function is now a tool that any AI can discover and use. Same for the resource. It's incredibly elegant. And the client side? Yeah, just as elegant. The client connects to that server we just made, it initializes a session to see what tools are available, and then it just calls the tool. Session.callTool, give it the name add, pass in the arguments, and you get the result back. That's it. No custom API mass, no complex logic. It just works. Okay, but wait. Anytime you give an AI the keys to, execute code and access your data, a huge red flag should go up. Security.
If you're going to build with this stuff, you have to be thinking about security from the very first line of code.
I mean, let's be real here. If an AI can just call any tool you give it based on a user's prompt, what's to stop a bad actor from tricking it into doing something malicious? This is called prompt injection, and it's a huge deal. You need a real strategy to defend against it.
Right, and this is super important. There is no one magic fix for this. The answer is what we call defense in depth. You need layers. You need a gateway to scan for bad stuff before it even hits the model. You need proper authentication, like JWTs, to make sure only the right systems can use the right tools. You need to validate everything coming in and going out. You should use a secure registry, so your AI only uses tools you've approved and signed. And finally, you need constant monitoring with a tool that watches your logs for anything that looks weird.
Let me show you a really simple, practical example of what I'm talking about. This little Python function is a basic filter. It just looks for common trick phrases, like ignore previous instructions. If it sees one of those, it just throws an error and stops the request cold. It's a simple first line of defense, but a really important one.
Okay, so to really get our heads around how these agents can think, we've got to go back in time, like way back. Back to the very first idea of what an artificial brain cell could even be.
So picture this, it's 1943. Two researchers, Warren McCulloch and Walter Pitts, published this groundbreaking paper. And their goal was nothing short of creating a mathematical language for how the brain itself works. This single paper basically laid the foundation for the entire field of AI. And out of that paper came the McCulloch-Pitts neuron, or the MP neuron. This thing, it's basically the first ever mathematical model of a brain cell. It's like the atom of artificial intelligence, a super simple little unit that can only make one decision, yes or no. So, how does this little atom work? It's actually dead simple, just 5 little steps. It gets a few inputs, which are just zeros or ones. Each input has a weight. The neuron adds up all those weighted inputs to get a total sum. It then compares that sum to a fixed threshold. And if the sum is big enough, if it meets the threshold, it fires a 1. If not, it just stays off and outputs a 0. That's the whole thing. It's kind of wild to think that this simple model from the 40s is the great-great-grandfather of the huge neural networks we have today. So let's connect the dots and see how that original concept shows up in modern code and ties back to the powerful agents we were just talking about. And look at this. This is that whole idea from 1943, right here in a few lines of modern Python. It's just so simple. The class takes in some weights and a threshold, and that activate method does exactly what we just described, sums up the inputs and spits out a 1 or a 0. This tiny class is the direct ancestor of today's most powerful AIs. Okay, so what can you actually do with a thing this simple? Well, you can build logic. Let's take a basic AND gate. As you know, the output is only 1 if the first input and the second input are both 1. And check this out. We can build that exact logic with our little Python neuron. If we just set the weights to 1 and the threshold to 2, we get a perfect AND gate. Think about it. If both inputs are 1, the sum is 2, which hits our threshold, so it fires a 1. Any other combination, the sum is too low and it stays at 0. This is computation in its purest, most basic form. So let's just pull this all together. It's an amazing story, really. This whole journey started with a model of a neuron so simple you can write it in 5 lines of code. We scaled those up by the billions to create today's powerful large language models. But they were still stuck in that box, totally useless for real-world tasks, until a simple, standardized protocol like MCP gave them a door to the outside world. And now today, we use all these principles together to build powerful, secure AI agents. And that kind of leaves us with one big final question to think about. The MCP neuron was the fundamental building block for the first era of AI. It seems like MCP is becoming the fundamental connector for this current era. So the question is, what's going to be the fundamental building block of the next one? It's fun to think about. Thanks so much for joining me for this explainer.